It's my pleasure to introduce to you today our guest speaker for a new feedback colloquium, who is Ludovic Berthier. Ludovic Berthier is a director of research at CNRS, the French National Center for Scientific Research. In the last year, he has investigated mainly in statistical physics at the Charles Coulomb Laboratory in the University of Montpellier. I think he's moving to Paris this year, in Montpellier. He's also a research associate at Cambridge University. He's author over 200 publications, and if I'm not wrong, in last March he was awarded CNRS Silver Medal for 25 years of research into disordered physical systems. Doing now a flashback to this, to the beginning of those 25 years I mentioned, he began his PhD thesis in theoretical physics at the end of the 90s at the École Normale Supérieure in Lyon, France. He focused his thesis on vitro systems, window glasses, emulsions, etc. His thesis was awarded the Saint-Gobain Young Researchers Prize by the French Physics Society. It was followed by a Marie Curie postdoctoral fellow at Oxford University. In 2004, Ludovic obtained a position at the CNRS. As I mentioned, he settled in Montpellier. In 2007, he was a visiting scientist at the University of Chicago. And from 2019 to 2020 at the University of Cambridge. Also, let me mention that in some coupling.
It's yours now.
Stefan is coming to the rescue.
We have to just stay.
I close mine.
I was saying that in 2012, he was awarded his first ERC, European Research Council grant. More recently, he has taken part in the international scientific collaboration, Cracking the Glass Problem, financially supported by the Simons Foundation in the USA. Now, talking more specifically about physics, Ludovic is a well-known expert on the physical glasses, of course, especially in statistical physics aspects and computational techniques to study them. Particularly, his work has caused a great impact in our glass community in 2017 with the development of the Swap Monte Carlo algorithm to rapidly prepare glass forming systems with very long realization times. So we experimentalists on glasses have known and have claimed for decades that the glasses obtained by computer simulations were too far from real glasses. The reason is that the time steps in molecular dynamics simulations are extremely short, and hence the typical Coulomb rays attainable for making a computer glass from the liquid amount to billions of Kelvin per second. In other words, the challenge with solid systems is to successfully simulate the very long time scales over which they evolve using faster algorithms. And the Swap Monte Carlo method developed by Ludovic's group has to a great extent overcome the difficulty. Well, I expect he will comment on this along his talk. So let's go. The title of the colloquium is very much pertinent and fascinating, in my opinion. Is glass a state of matter? We are eager to hear the answer. And okay, Ludovic, the stage is yours. Thank you.
Okay, so we can. Okay, this is working. So thank you for the invitation. Thank you for the very kind and detailed introduction. So it's my pleasure to be here. So indeed, the question is a bit broad, and I hope simple and appealing to all of you. So what I'm trying to do here, I will focus on the sub-part of the research we do on the glass transition and glassy systems, and I will address really the deep statistical physics question. Is it from the interactions between the particles, can something like it, similarly to a glass or liquid or to a crystal, to a liquid or gas, is there something that we can call a glass that's truly is produced by crossing the phase transition, free energy minimum in equilibrium conditions, homogeneous phase of matter like all the others? So that's the question of today. So I mentioned briefly the collaborators, which are both working on this very questions and also have developed this algorithm that I'm going to mention before. And this was all, I think, a large enterprise of theoreticians trying to understand better at the core the question of the glass transition problem over the last years. Okay, so I'll start with, so the question is glass a state of matter? So I have one slide of crash course on statistical physics, thermodynamics, and states of matter and phase transitions. So I hope this is not too insulting, but I restart from the basics. So this is my favorite book on thermodynamics. It's the Callen first year book. And I start from the law of ideal gases, and I'm going to give you all the keywords. It may look simple, but I will use all of them later, so be careful. So we know that phases of matter, first of all, emerge when we have a large number of particles. It's a collective effect, otherwise nothing interesting really happens for us. And they also emerge because particles interact. So when you don't have particles interacting, you have ideal gases, and you know that, this is boring, it's a gas, you don't have phase transition. The minute you start introducing interactions between them, this is the first correction that everyone has learned. It's the van der Waals equation of states, where you introduce a little bit of attraction between the particles. The pressure is a little bit reduced. The minute you go from the, in the PV plane, you have P 1 over T, 1 over V for the ideal gas. The minute you go to the van der Waals, you discover this, that at low enough temperature, the isotherms have an instability, and this instability is nothing but the liquid to gas phase transition. So attraction introduces the liquid. So first lesson, in many body interacting systems, interactions produce new physics, new matters, new states of matters, and this is the left part of things. Then we learn how to do phase diagrams, study phase transition between these various phases. And in a pressure temperature plane, we have the phases of matter that we know. At high temperature, low pressure, we have the gas, which has a transition to the liquid. And the liquid may crystallize at low temperature into a solid. And this is the phases of matter that hopefully we all know. So the question we ask is there something like a glass phase hidden somewhere in this phase diagram that you don't learn in the Callen textbook? But this is what I want to tell you about. So again, all these considerations in the book are done in thermal equilibrium. You never invoke the dynamics of the molecule to just look at the static properties, the thermodynamic properties. So kinetics is totally out of these considerations. You don't talk about that much later in statistical physics. And of course, as Michael introduced, for gases, the dynamics is important. So that's a key distinction. We know, of course, because we have learned about phase transitions, that phases are distinguished by their symmetries. You have usually order parameters that are changing between, say, the liquid and the gas. It's the density, which is the order parameter. And between the liquid and the solid, it's the crystalline order that emerges at the melting transition. So these are equilibrium phase transition between phases that you can distinguish by order parameters. If we want to study them theoretically, we have to go to this kind of diagram where I have a free energy plotted as a function of the order parameter, and that has the name of, say, a Landau description of phase transitions, where your free energy or your whatever thermodynamic function is expressed as a function of your order parameter. For the liquid gas, it's the density or the volume or whatever. So what we have is when we have a first order transition at coexistence, we have two minima that have the same free energy. And we know that when we approach the critical point here, the distinction between these two minima becomes small and small and small. And we have this specific, very interesting point here, which is a second order phase transition. And this is again something that I'm going to use, first order and second order phase transitions. It means this endpoint here has been the focus of hundreds of studies in statistical physics. It's the study of critical phenomena, second order phase transitions, where you have interesting fluctuations, critical exponents, and also universality, which means all liquids essentially behave the same independently of the molecules you're studying. And this is the types of questions we are going to ask about the glass transition. And these are the tools that I'm going to use in the future. So the question now, where are glassy states? Clearly, we don't hear this is gas, this is not glass. Okay. So let's move on to what glasses are. So we know glasses, we've all seen glasses, we've seen glass blowers. So what do? They heat their favorite glass forming system, mostly silica, in their ovens. You have this orange thing, which is very viscous. They take it out of the oven. It's a liquid. So it's pretty like the liquid phase I mentioned before. And very gradually, the liquid, as it cools down, becomes more and more viscous gradually. Okay, and during the cooling, the artist is going to shape it because it's a bit liquid. But then as the temperature goes down, it's transforming gradually into a solid. The viscosity becomes so large that what was easily distorted into this liquid shape drops, it's becoming a solid. And this is a piece of glass. You've all seen pieces of glasses, it's a solid. So we have a transformation between the liquid at high T into the solid at low T. The solid has sort of a memory of the liquid, but it's truly a solid. And this is the glass transition as we know it from glass growing systems. And this is the glass transition as observed experimentally since hundreds of years. So what's the difference between the liquid and the crystal in terms of what the atoms or the molecules or the constituents are doing? The crystal would have this perfect periodic order where the atoms, have this order at the local state. In the glass inside, the particles are completely messy. They are dense, homogeneous. The density field is not, you don't have holes or something like this, but it's totally disordered. So the glass, in a sense, this is what I told you, they have the disordered structure of the liquid. They have this memory of the liquid state of which they come from. But they also have the rigidity of crystals. And we know that, glasses are solids. You drink in glasses, and these are pieces of solid. So this is then already interesting as a solid state physics problem. How do you compute any physical property of a glass? Do you start from the liquid state? Do you start from the crystalline state? None of this starting point is right because the glass is right in the middle. So when you start your solid state physics calculations and lectures in second or third year, I don't know, you open the books of Ashford and Mermin or Kittel or whatever is your favorite book. Not a single chapter is dedicated to glasses because everything is constructed based on exploring the consequences of periodicity. And this is where it all comes from. In glasses, you don't have this, so the problem of the properties of the glass are complicated. So one property that I like to mention in all the talks, not only when Michael is present in the first row, is think about the simplest property of crystals, the specific heat. When you start to combine solid state physics to statistical physics, the first calculation you do usually is the Debye-Einstein model. You start from this, you look at harmonic excitations, you explore the eigenmodes, they are called phonons, and you do the statistical physics of phonons. This is what Debye-Einstein did, to predict that by the phonons, you will predict that at low T, the specific heat is T cubed in crystals. In experiment, as is well known, especially in this department, it's measured that the specific heat of glasses is not T cubed, but T, which means that even the basic excitations of glasses are very different from the ones of the crystal. And today, I think there are empirical models, but there is no analog of the Debye-Einstein model for the specific heat of glasses. It's a totally open problem. It's not in textbook because it doesn't exist. It's one of them, and there are so many of them that exist in the field of the glass transition. Okay, so bottom line is when we want to understand the properties of something, we need to classify it in a phase. And when we know the phase, then we can start and explore the consequences of the phase. And this is that curve. Okay. So I'll be focusing on very, very simple models for atomic or molecular glasses. But I've spent quite a bit of time in my career exploring also the physics of more complex systems, as we like to call them. And for me, dense assemblies of colloidal particles or cells or even animals, when they are compressed and they are dense enough, what I see in all these three images is dense things that behave as solid and are disordered. So to me, they are all called glasses. So I call glasses all of them. And of course, when I go to a conference where people love to talk about biophysics systems, I don't mention too much the glass transition, but this is how I think I like to think about them. And this is, I think, an important point to make in any glass talk, that it's much broader than simple molecules. That has been articulated much before me, so that's the famous quote that we all use in ground applications. So usually we use that sometimes from Phil Anderson, solid state physics, telling us that this is the most important problem on Earth, okay, the glass transition. This piece is really interesting. It contains additional sections that are very nice. So one section is about the spin glass problem that was, a hot topic in the 70s and 80s. And the realization that if you solve the spin glass problem and you understand the properties of these complex disordered magnetic systems, you also understand lots of things about more complex systems and many applications. And this is nearly what the Nobel Committee has written to award the Nobel Prize to Giorgio Parisi 2 years ago, the implications of this spin glass calculation that we did. But Phil Anderson also talked about the glass problem itself, the one I'm interested in, and he also said that it's an interesting problem, that solving it will be complicated. And with a little bit of irony, I think he's challenging the community that maybe this is totally useless. So I think one possible answer to this, is it useful to do glass research? Can you produce something that's, a better glass? And one answer that I like comes from this work on our colleague and collaborator Mark Ediger in Madison, who introduced this technique of physical vapor deposition to produce glasses. So instead of taking a liquid as the glass blowers do and cooling it in the bulk, what he's doing, he's preparing a substrate and he's shining the vapor directly. So the vapor transforms into the solid directly. Okay? And if you adjust the speed at which the particles are coming and the temperature of the substrate well enough, and you have to explore this is what they have discovered in this paper. The Tetris analogy tells you that if the molecules arrive very, very slowly, you will find the time to, produce a packing of the molecules that's very, very efficient. And many years of work in that discovery has proven that these glasses truly behave as a different material, as better glasses. They do behave as if the glass blowers were cooling their samples many orders of magnitude slower than what is usually done. Million years old glasses are being produced in one afternoon in this experiment. And there are many papers and exploration trying to prove that the improved properties of this may find applications anywhere in applications and research. And Miguel has done work to prove that if you study the specific heat of these systems, they do behave as the specific heat of crystals, as if these surprising glassy excitations had completely disappeared. So to me, this is another proof that these glasses are different, they are better in some way, they have different excitations, and they are very interesting. So this is the broad introduction about glasses, and just to give you a few things. Now I go back to this idea of, I told you about simple phases of matter, I told you about glasses, so now I'm putting everything together in the same diagram. So what I have is something like the density or the volume of the system as a function of temperature. So I started in the first slide by recalling the gas, the liquid, and the crystal. All of this, for water, for instance, you have the gas, the liquid, and the crystal at 0 Celsius. So where are glasses? So glasses are systems that in the liquid state don't easily crystallize and they remain just liquid. And this is the thing that the glassblower are trying to shape into an artistic shape. So this is the supercooled liquid. That's the system which is becoming more and more viscous. And at the experimental glass transition that I'm going to describe in a minute, the motion of the molecules, or equivalently the viscosity of the system, is so high that the system is effectively on experimental timescale behaving as a solid. So you have something a little bit viscous, extremely viscous, and so viscous that it's difficult to distinguish it from the glass. If you cool it a bit slower, as we discussed already, you get like a better glass, slightly denser glass, a better packing, and the ultra-stable glasses would be much better than this. But it means that the glasses you prepare depend also on the way you have prepared them. So in a sense, what I'm giving you here is already an answer to my question in the title. Are glasses states of matter? No, because they don't satisfy any of my criteria. They clearly don't have crossed like a well-defined phase transition between the liquid and the glass. They are non-equilibrium states. They slowly evolve and depend on the way you have prepared, so they depend on the kinetics. So clearly, for the conventional glasses, the arc shapes that I've shown you, the answer to the question of the title is no. And it's very clear and very simple because from the viewpoint of statistical physics, it's not a phase. Okay. But boring, that could be the end of the seminar. So of course, the question is a bit more interesting. So here, the system transforms experimentally into a solid because the molecule takes so long to rearrange that I don't see them rearranging anymore. But if I could wait much longer, maybe they would rearrange, and maybe I could, keep the system in thermal equilibrium, exploring ergodically its configuration space, and maybe something would happen somewhere. And this is what I want to discuss today: the idea that maybe somewhere that is not easily accessed by this experiment where you cool a system, somewhere something like a real, genuine equilibrium phase transition between two phases of matter could happen. This would be the liquid, and this would be the glass. So this is what I want to discuss next. Is this phase transition a reality? Is it real? Can it exist? What do we know about it? So that's the next question that I want to address. But for the ordinary glasses, they are a mess. Okay, so why do we think that something like an ideal glass phase transition between the liquid and the glass could exist in equilibrium conditions that I've mentioned before? It goes back at least 70 or 80 years. So I should have mentioned that the glass transition temperature, we call it the Kurtzman temperature, and it comes from this historic work of Kurtzman published 70 years ago. So what Kurtzman did at the time was the following. He was collecting, I think, experimental data from thermodynamic measurements made in several systems that undergo glass transition. And this is the plot he produced. So he compared the entropy of these liquids as they approach the glass transition. And he compared the entropy of the liquid to the entropy of the corresponding crystals. And he gave a name to that difference, but let me call it for today the configurational entropy. So it's the entropy that the liquid has in addition by difference with the one of the crystal. So the first idea you would have is the crystal is a perfectly ordered state. So if you think that entropy is a measure of order, the liquid is much more disordered than the crystal. So this difference is positive. So we are counting how much more disordered is the liquid compared to the crystal. And this is where the surprise comes from. If you rescale that thing such that you start from 1, for all the liquids to absorb the prefactors from experiments, you see that this difference drops very sharply as you approach the glass transition. And of course, here at the experimental glass transition, your experiments stop because the system stops exploring in equilibrium conditions configuration space. So experimentally, you're blocked into the liquid, and at TG, you can't do experiments anymore because thermodynamic measurements, entropy measurements require equilibrium, and the system falls experimentally out of equilibrium. Yet, you have a line, so it's tempting to try and extrapolate it. And for all of them, if you do this extrapolation, it hits 0 at some temperature that we now call Kurtzman temperature for that very reason. So there is a hint that this entropy difference between the liquid and the crystal goes to 0 at finite temperature. And if you think again of the entropy as a measure of disorder, you have a liquid which is totally disordered, but has as low an entropy of the perfectly ordered crystalline state. And that's a surprise, that's a paradox. Sometimes we call it the Kurtzman paradox. And then we have to think about how to understand that entropy rises as we like it, the fact that this liquid has no entropy at all. It has the same entropy as the crystal, and the crystal has no entropy at all. Okay? So that's the paradox. And this is the idea that maybe there something like a glass state with 0 entropy exists. Right? So this is what we want to explore. Goes back 70 years, so you can imagine how many discussions and papers have appeared into this. So why don't we have an answer experimentally about this question so far? This is the question of the dynamics now that comes in a sense, from the viewpoint of statistical physics. It's a nightmare, it's a mess, it's polluting our measurements. It's also an interesting physics problem, but today I won't talk at all about the dynamics because I want to do thermodynamics and statistical physics. Yet I think one slide about the dynamics is good enough. So again, what I told you is that as you approach a glass transition, the molecules in the system relax slower and slower. And this is a measurement of how slow the molecules relax, taken in many different types of molecular glasses. So typically, people measure something like a correlation time for the orientation of the molecules by dielectric susceptibility, for instance. And you plot the log 10 of this relaxation time, and you see the number of decays that you have. And this is plotted as a function of 1 over the temperature. So low temperatures are on the right. So what we have is that in high temperature liquids, you have typical timescale for molecular motion in the picosecond regime. So we are talking about molecules reorienting in the liquid that would take 10 to the 12, 10 to the minus 10 seconds roughly. But of course, as we approach this experimental glass transition, I told you molecular motion slows down a lot. And by a lot, it means by instead of having picoseconds, you have hundreds of seconds or even more if you are patient enough to measure these things. So this time scale that was so short, so microscopic at low T in the liquid becomes gigantic at the experimental gas transition, meaning molecules stop moving essentially because they take forever to even do something like this in the liquid. So what is the consequence for us today? It means that the configuration is stuck and the system goes nowhere. This is the solid, this is the piece of glass that we like to drink wine out of. But it means in terms of sampling configuration space, doing statistical physics, being in equilibrium, the system is dead. It's not ergodic anymore, it's not equilibrated anymore because the relaxation time is much longer than the time scale of the experiment. So again, told you, it's a really interesting, fascinating physics problem to understand these dynamics. Not today. Today, it's only a terrible burden because the system falls out of equilibrium and we can't answer our question. Okay. So if we want to make progress, we need to avoid that dynamics problem. And so this is what I want to do in that seminar. I want to give you two solutions to how to avoid the dynamics problem, this bottleneck of the molecular motion following out of equilibrium in two ways. The first way will be I do calculations, I do statistical physics, I write the partition function as usual as a sum of a configuration space. Here, as I mentioned in the first slide, time never appears. You just assume that you have a configuration space, then you do your calculations. This is what you do for ordinary problems. This is chapter 3 in my talk. The chapter 4 will be how to use these algorithms that Miguel mentioned in the intro to bypass the dynamic slowdown and try to do statistical physics calculations in computer simulations of liquid. Okay, so let's try by doing statistical physics. And usually, if you remember the second chapters after this phase transitions I showed you, you start and do simple calculations of simple phase transition in simple models in these books of standard first year statistical physics. And typically, you can't do calculations because many body interacting problems are complicated. So you have approximations. And this is where I think students get lost because they don't like approximations at all. This is where we stand in the field of the class transition. If we want to understand the statistical physics problem of many body interacting systems, so you have a bunch of hard spheres or Lennard-Jones particles or something, this is your model that you want to solve. At the moment, the only thing we can do is derive a mean field approximation for this statistical physics. And this is what has been done. So mean field approximations are, a common word in statistical physics. What I think has been learned in the last few years only, that if you do these broad approximations to the statistical physics of liquids, it's now known that it's becoming formally exact when the number of dimensions of space goes to very large. So again, I told you about critical points and critical phenomena in the first slide. I think many of us know that in large dimensions, above 4 dimensions or 6 dimensions, mean field theory for the values of the critical exponents of light. It's a bit like this here, that in large dimensions, the problem becomes a bit simpler to solve. And this is what's been done in the last 40 decades. So what is the bottom line of all this? There are a very solid starting point to understand the statistical physics of the glass transition. There is a very solid mean field theory. It's unique. It's the mean field theory of the glass transition. It's an exact solution in large dimensions, and you need to be sure that it has something to say about finite dimensions, as in ordinary statistical physics problems. It's so hard and heavy and technically involved that it took decades of hard work to get there. And that has been, I think, summarized in that book 3 years ago by Berthier and co-workers. Really hard work, but very solid, very nice and elegant, and very solid mathematically because there is a limit where it's all exact. So we have a starting point to think about this phase transition in finite dimensions. And what is the bottom line of this mean field theory? The bottom line is that in large dimensions, you can show, and it's a result now, that this Kaufman transition to an ideal glass state, it exists, it is realized in large enough dimensions. And because we can compute everything about it, we know everything. We know its order, it's looking like a first order transition. We know the order parameter, we know the free energy behavior. So everything I've shown you about the van der Waals equation of state in slide 1, I'm going to show it again for now the problem of the glass transition as computed on mean field prediction. So we know everything in that mean field limit. So of course now we have to go back to finite dimension. So how does it look? So we have to think about how to distinguish the liquid and the glass phase. First of all, we have to know and understand what's the order parameter first. So that was the density for the liquid gas transition. That was crystalline order for the liquid to crystal first order transition. What is the order parameter between the liquid and the glass? So let's go slowly over this. So the key word into this, it's called the overlap, and the overlap Q in the following will be the order parameter telling me the difference between the liquid and the glass across this first order Gaussian transition. So normally when you want to decide what is the phase of the system, you take one configuration, you look, it's very dilute, it's a gas, it's very periodic, it's a crystal, or it's a dense liquid. If you take a configuration in the liquid and a configuration in the glass, and you take just one, you can tell. Okay, so the difference between the liquid and the glass, you can see by the eye in single configurations. I think some people in my field would disagree a little bit, but for today, I think it's good enough. So what you have to do to think about this overlap is you have to take two configurations now. And so the construction, at least for the talk today, it's good enough. You draw one configuration from the Boltzmann distribution. You draw a second one totally independently, equally well equilibrated. And now what you have to do to construct this overlap, you have to look at how similar or how different they are. This is why it's called an overlap. It comes from the physics of spin glasses, for those of you in the know. And pure, this overlap would be essentially zero. The configurations are totally different. And that overlap would be very close to one if the two configurations, if the two density fields, if you wish, look very much like one another. So why is this overlap order parameter a good idea to think about the Gaussian transition? This is what I want you to digest. Okay, so I told you that the Gaussian transition, as invented or guessed by Gaussian, was related to this entropy crisis, the fact that the entropy goes to very small. So what Gaussian told us is that in the liquid, there is a finite amount of entropy. Entropy means number of microstates. And so what do we have in the liquid? We have a finite entropy, we have plenty of microstates. So if I take two at random, they're very different. Instead, in the glass phase, where we have this entropy crisis, entropy is zero. So the number of microstates is very small. That means if I take two microstates at random, with a high probability, they will look like one another because they are one and the same configurations. So lots of entropy, lots of configurations, they are all different. Zero entropy, very small number of configurations, they're all the same. So the overlap is one and the overlap is zero, with something happening in between, which is the phase transition we observe. And this is what it's looking like when you explore and you express the free energy now as a function of this newly defined order parameter. And it's looking like my slide one, but now adapted to the context of the glass transition. So I write down my free energy as a function of the overlap, not the density of the crystalline order. And in the mean field limit, I can compute that quantity, and that quantity has this beautiful name transparency by the two guys who first computed it. Okay. It's the exact analog of this G versus volume that I showed you in the first slide. And indeed, it looks the same. This is why I chose the Canadian textbook. So it means you recover this idea of metastable states that appear near a first order transition. So at temperatures above the Gaussian transition, it's the liquid that has the lowest free energy minimum. So it's dominating the free energy, and its overlap is close to zero, as I told you before. And the glassy state, it's there, but it's metastable, and it's not yet the equilibrium phase. You decrease the temperature towards the Gaussian transition, and then you would have this coexistence of states, and then the system is going to jump to the glassy phase discontinuously. Okay, so that's the very same picture of the van der Waals slope that I showed you for the liquid gas transition at the beginning. It means if you follow the average overlap, you're here at high temperature and you jump there discontinuously at low temperature. And this is what the overlap is doing, is jumping discontinuously. So it has all the flavor of a first order transition with an order parameter that becomes discontinuously non-zero below the transition. And the cool thing, and this is where everything I think wraps up so nicely, that An interesting quantity, of course, to characterize this first order transition is the free energy difference between the liquid in equilibrium and the glass, which is metastable. And it turns out that this free energy difference that continuously goes to zero when the green curve is approached is the configurational entropy of that system. So this is what I was telling you, the configurational entropy. That thing goes continuously to zero, the Kraussman transition, and remains zero. So this is the glass, this is the liquid, entropy, no overlap, large overlap. And this picture the first order transition like in the first slide. So this is how the glass transition, the equilibrium glass transition looks like in the context of mean field. It's looking like the van der Waals picture that I showed you in the first slide. So this is the slide where we go one step further, and this is the slide also where the students don't like it. Remember, in the thermodynamics, we have pairs of conjugate variables, so we can use pressure or volume, we can use magnetic field and magnetization, etc. And we change variables, we do Legendre transforms to express, your control parameter, which is one on the other. We can do exactly the same. So I introduce Q, but I can also introduce the field conjugate to Q, and we used to call it epsilon in that field. It's really the same. I change, I do my Legendre transform by changing variable. And now my control parameter is epsilon instead of Q. Again, you can control volume or pressure in a liquid. It's equivalent. You can control Q or epsilon. It's your choice as an experimentalist or theoretician, so use one or the other. The reason we like epsilon is the following. We can now expand the phase diagram into temperature and epsilon, which is my control variable. And this is, I think, a better analogy again with the van der Waals picture of the first phase. So remember, when you don't have that field, you decrease the temperature, you have that Kraussman transition that I described in the previous slide. Now imagine that you have a tool like an experiment to introduce that epsilon field. So that epsilon is favoring low values of Q because when you put epsilon, if Q is large, your free energy decreases. Okay? That means epsilon has the tendency to promote large values of Q. In other words, it means if you start from this temperature and you put my epsilon Q, you're going to tilt that phase transition like this by an epsilon Q factor. So that field epsilon is taking that curve and trying to make the glass more and more stable because it has a large overlap. And if you make the glass more and more stable, eventually you will jump discontinuously to the glass. If you're above the Kraussman, but you apply that field again, you fall into this glass transition, this glass phase. So what it does, this epsilon, it's now provoking the emergence of a first order transition line. And so the metastability of the glass close to the glass transition transforms into the emergence of this first order transition line. So the yellow things here is a line of first order phase transition between small q, large q discontinuous. And of course, when you increase the temperature, the difference in q here becomes smaller and smaller and smaller and smaller. And it disappears, guess what, at a second order critical point, above which there is no transition anymore. So here the analogy with my first slide is perfect. We have this line of first order transition which ends at a critical point. And that's the complete mean field picture of the glass transition. So when we do experiments again, we are stuck in here and we try to approach as close as we can the Kraussman temperature, but we need to extrapolate. In the calculations, we can go anywhere because we avoid the dynamics. And in the calculations, we can even introduce this artificial field that you cannot do in an experiment. And we have a more complete phase diagram which summarizes everything, that is essentially this first order nature of the phase transition. So what's cool about this is giving us many tools and quantities and ways of thinking about the same problem is, does this guy exist? And the fact that this guy exists as a first order transition has consequences in the plane, in this expanded plane, and this is what I'm going to do in the next chapter. Okay, so that was the theoretical part. So what's the situation? So answer to the question, is there a glass phase somewhere? The answer is extremely clear and everybody agrees on it. If the space has many, many dimensions, in there we know everything. Okay? And the answer is a clear yes. And that hasn't been an easy road, but people have managed to do it and are still working on this mean field theory to predict more things. So of course, now the big challenge is how to go back from large dimensions to finite dimensions, and how to treat the fluctuations that appear in finite dimensions analytically. So people are trying this. Anything could happen, small corrections, big corrections, gigantic corrections, everything wrong in finite dimensions. We know that from studies of other critical phenomena. Some things easily survive and some things don't. And you don't know a priori unless you are able to compute these perturbations. The only thing we know already is something like this. We know a few things. We know the nature of that guy, and I'll show you in a minute. We have good ideas to think that this critical point disappears in 2 dimensions. So even without measuring or thinking about anything, there is this idea that 2 dimensions should really play a special role for the statistical physics of the glass transition. So I told you everything about B equals infinity. I told you that anything could happen in finite dimensions. We need to go back and test these predictions in finite D. And this is where you cannot do, your statistical mechanics calculations anymore, but now you have to solve this slow dynamics burden again. So how do you do it? This is where you introduce your algorithms to beat the dynamics again in finite D liquids. Okay, so this is what I want to do now. I want to show you that because of these new algorithms that exist, we can really go much lower in temperatures. We lose information about the dynamics, but we keep, very importantly, information about the statistical mechanics. Okay. So I don't have much to say about the swap algorithm that was mentioned in the introduction, but it goes a little bit like this, and this is the only useful information for today. So when you measure the relaxation time of your molecules or particles in the computer simulations versus 1/t, so I showed you the equivalent slide for molecules before. So remember, the molecules were slowing down by something like 12 or 14 orders of magnitude between the high T liquid and the expanded gas transition. If you do conventional computer simulations that follow the physical dynamics, you start the same as molecules, but then you have this colossal gap between the timescales that you can reach in the computer simulations and the experimental timescale that I mentioned before. So what the swap Monte Carlo does for you is giving you a way to access equilibrium quantities into a time that's much shorter than the physical dynamics. So you beat the dynamics completely. And for instance, for this particular example of this particular model, at the experimental gas transition, where the physical dynamics take this 12 orders of magnitude of relaxation time, if you compute how long it takes for these Monte Carlo simulations to reach equilibrium, it takes about 2 orders of magnitude only. So you have speed up the sampling of your configuration space by something like a 10 to the 10 factor. And in 2 dimensions, we find that this 10 to the 10 becomes gigantic, extremely large. So I don't want to enter the details of this, but I want to give you the consequence for the talk of today. So the consequence is that the timescale gap, this physical problem that dynamics is very slow, that maintaining equilibrium is very complicated. It's solved to a large extent in computer simulations, and we can keep something equilibrium properties at extremely low temperatures. And this is what I want to do today. So it means there are many questions that we can try to address numerically, in particular comparing to experiments, for instance. What I want to do today is use that tool that I said nothing about to sample the equilibrium statistical physics property that I described that come from just theory. So that's the program for what's next. So what's next is the analog in computer simulations of 2D and 3D models of supercooled liquids of all these quantities that I showed you several times already. I showed you everything for the van der Waals first slide. I showed you everything for the mean field series. I show you the same quantities for the supercooled liquids in finite dimensions now. Okay. So the first thing I would like to show you is this Landau free energy, which I told you was called, in fact, the Franz-Palesi potential in our thing. It is, you have to do free energy measurements. So this is a free energy, and you have to measure the free energy profile as a function of your order parameter, which I told you is this overlap function. So if you remember, the overlap is this comparison between pairs of equilibrated configurations. It's been a nightmare to get there. It took us 10, 12 years of work to get to these figures. But now what we can do is we can directly measure totally in equilibrium this transparency potential in 2-dimensional and 3-dimensional systems. And we can do this for a relatively broad window of number of particles, so system size. Why is it important to vary the system size? I told you in the first slide, phase transitions only exist when n goes to infinity and things become sharp. Okay, so we need to think about finite size effect and the thermodynamic limit. So these are two examples in 3 and 2 dimensions. And typically we always see something like this, that if we measure this transparency potential at high T, we see that the liquid at low overlap is dominating. And as we decrease the temperature, we see the development of this secondary minimum at large Q. So that is, again, totally in equilibrium without extrapolating anything. We can see that something at large Q is starting to develop. And the system is trying to head towards something that looks an awful lot like a first order transition. So this is what we can conclude from these curves. We have directly in equilibrium, infinitely, the signature that the system is heading towards a first order transition. So we would love to cross it and show you the analog of the glassy phase, but in equilibrium, we cannot do this yet with computer simulations, but we are heading there, and it's very clear on this. Okay, so this is the transparency potential. I showed you something about the Kaufman transition, and then I told you about this weird epsilon field, and this is what I want to do next. So remember the Kaufman entropy at the beginning? It was this entropy difference between the liquid and the crystal. I told you in the context of the mean field theory, it's much simpler to understand. It's the free energy difference between the glass at large Q and the liquid at low Q. So this is what we do now. We don't go into entropy measurements at all. We go to these free energy measurements, and we measure the free energy difference between the glass, which is metastable, and the liquid, which is stable. So that's the free energy difference between the two phases. And what we construct then is a plot which is analogous to the plot of Kaufman, where all the curves start by 1 and 1 by rescaling the temperature and this configuration and entropy at high temperature. So the gray symbols here come from experiments close to the one of Kaufman 70 years ago. They come from really molecular systems measured experimentally. These are newer data, but nothing has changed anymore. So these are the very stable glasses that I mentioned from the group of Mark Ettinger, much slower, much closer to the ideal glass transition as before. The new thing and the thing that is very nice is those three guys, the red, the purple, and the blue, are 3-dimensional systems for which we measure the free energy difference between the metastable glass and the equilibrium liquid. And as Kurtzman had seen, we see that this free energy difference is dropping very sharply as the temperature decreases. And if we play the game of extrapolating, we have the feeling that something like a finite temperature Kurtzman-like transition may emerge. But now this time, these are from, again, these equilibrium free energy differences, so very well-defined quantity, everything measured in equilibrium in 3-dimensional simple systems. There's one outlier, which is the green one here. If we measure this guy and we try to extrapolate, we have the feeling that the extrapolation goes to 0. And that guy, interestingly, works in 2 dimensions. So we, from the measurements of these free energy profiles, we directly have an evidence that 2 dimensions is out of the other systems, and that 2 dimensions seems to play a special role in the sense that instead of having a finite temperature transition, it's being decreased to 0 temperature in 2-dimensional systems. That's one way of seeing it. I'll show you another way in the next slide. So now I go to my magic bullet, this epsilon field that I mentioned before. Again, what I did before, I didn't have that bullet. I was working by decreasing the temperature, trying to access that Kurtzman transition, giving you some evidence of it. I told you also from the mean field calculation, if that guy exists, gives rise to that guy, his first order transition line, because it's equivalent information. In addition, it gives rise to this non-equilibrium, to this equilibrium critical point, whose properties we understand pretty well from the viewpoint of the theory. Why is it cold? It's cold because this line exists at much higher temperatures. And so it means if I do the following construction, I go to as low a temperature as I can, and I will introduce my epsilon field. What I should see like a small overlap jumping discontinuously to a large one. And if I do this at too high a temperature, I would see just a broad crossover. And if I do it just right here, I would see interesting fluctuations. And the cool thing is that this is happening at much higher temperatures where simulations are much, much easier. So the bottom line, and this is what I want to show you, we can't get there yet, but we can get there already. So this is what I do. I construct the isotherms that I showed you again at the first slide of the liquid gas, and I do exactly this. I measure the overlap as I increase the field epsilon at different temperatures across this transition. So what do I see? I say that if I increase the field epsilon and I measure the overlap, I have a smooth evolution at high temperature. And if I go to low temperature, I have something like a discontinuous jump like this. So again, I go back one. I have something continuous, and then I have a discontinuous change of my overlap if I cross the blue line. So what I'm showing you here is direct evidence completely in equilibrium that by increasing that field epsilon, the overlap jumps discontinuously. So direct evidence here of the first order transition line without any extrapolation. The only thing that is an approximation now in that slide, it's not the dimensions, it's not the temperature, it's not the equilibrium, it's that guy n. The number of particles is finite, so I want to convince you that this is a phase transition. I need to send that guy to infinity still, okay? So these black squares, if I see them, I look at here and I look at the overlap, at the probability distribution function of my order parameter, I see something that's broad and boring and Gaussian. If I sit in the middle of that line, I see like a bimodal distribution. What does it mean? It means if I want to put my system here, what it does, it's phase separating between two phases, the large Q, the low Q, just as liquids and gas phase separate at coexistence. That's the exact same thing. So this bimodal distribution at coexistence is telling you this is the first order phase transition. And of course, the cool thing is that if you are right there near the critical point, you have broad fluctuations of your order parameter. It's a second order critical point. So everything is cool qualitatively, but still we have that guy and we need to think about the thermodynamic limits to finish the job. So this is what we try to do. We start to do it in 2 dimensions. So we do the following construction. So we want to take the thermodynamic limit. So we now increase the size of the system. We say that for some specific temperature system size, if the system is phase separated with 2 peaks, as we increase the size of the system, it goes back to 1 Gaussian distribution. So what looked like the first order transition for finite n disappears when we take n going to infinity. And when we do this for as low a temperature, as large a system as we can, it always disappears. So our conclusion from these extensive studies is that in 2 dimensions, we don't find the blue line, we don't find the blue bullet, we don't find the Gaussian transition because the Gaussian transition is suppressed to 0 temperature. And I told you this is maybe expected from the physics of the mean field theory that I mentioned you before. It's a totally non-trivial prediction that all these measurements should really show this behavior in 2 dimensions. So this agreement with the mean field approach of the gas transition, you go to 2D, it looks like you have a phase transition, but you have nothing. It disappears by fluctuations. It's really a non-trivial prediction and non-trivial test of the theory. We do the same job in 3 dimensions, and we again try to reach the thermodynamic limit. So we start from this probability distribution that is bimodal. We took the log now because this is going to be very, very small in the middle. So we have that bimodal thing. We make the system larger and larger, and this is becoming more and more bimodal. So for the system sizes and the temperatures where we can access and explore the approach to the thermodynamic limit, we have all the signs that people have gotten in ordinary phase transitions, that the system is truly having its first order phase transition in the thermodynamic limit. If we look at what the system does in real space, when you try to put it in the middle, it's phase separate macroscopically between a large Q and a low Q phase. So this is phase coexistence in real space in a 3-dimensional system now. So the simulations, they do confirm the emergence of this first order transition. So this is the blue line emerging. And the final slide I have is one slide about the critical point itself. So we did try to work a little bit to derive the critical exponents that control how fluctuation susceptibility diverge near the critical point. And the prediction we have from the theory is that the exponents should be the same ones as this mysterious acronym, which is called random field-izing model. So the universality class that comes from this ordered magnetic system is predicted by theory to apply to three-dimensional liquids. We couldn't measure the exponents directly, so what we checked is we use finite size scalings to show that if we use the exponents of the random field-izing model that come from lattice spin model with these orders, they do describe the fluctuations in the liquids perfectly. Okay? So we do find good evidence for this critical point and relatively reasonable evidence that the critical exponents are the one that we expect from the theory. Summary again of everything. So I summarize everything into these temperature epsilon planes in 2 dimensions and 3 dimensions. These are the simulations, and this is the picture that emerges from all of this. So again, if we look at 2 dimensions, we decrease the temperature, we look at the entropy, it wants to vanish at 0 temperature. We introduce that epsilon, we find a crossover, but it disappears at large n. It's just a crossover. It's not anything like a first order condition. So the plane in 2D, it's totally boring with maybe something existing at 0 temperature. And this is the picture that emerges. We have that crossover that disappears in the thermodynamic limit. And the system remains, a liquid down to 0 temperature where maybe the Kurtzman transition happens. In 3 dimensions, it's different. So we have the hint that when we decrease the temperature, the free energy wants to vanish at finite t. That's the Kurtzman transition. If we look at the influence of epsilon, we see nothing but a crossover at high t. We see this interesting critical point emerging, below which we have this first order transition that survives the thermodynamic limit. So the picture that emerges is consistent with this simulation. It's something like this, with a glass transition that exists at finite t, the liquid, the glass, this line of first order transition, and this second order critical point, everything being now in 3 dimensions and not in large dimensions as before. So this is the picture that emerges from the simulations. This is totally consistent with extrapolating from large dimensions and coming back to finite dimensions. Okay, so I try to summarize and stop because it's time to finish. So was a glass state a state of matter? I quickly answer for the conventional glasses that we use now. Is this something, does something like an equilibrium glass exist? I gave you 2 answers. I told you if you go to large enough dimensions, of course it exists. And something like a liquid to glass phase transition exists with properties that I try to share with you. And this is done, this is finished track. This is all well known and understood and accepted. So the big question, of course, is what's happening in real liquids, experimentally or in finite dimensions for computer simulations. We have reasonable evidence for that picture. Of course, the systems are never large enough, low enough, And the one thing I could not do in the simulations is to explore that blue line and cross that green point in equilibrium conditions. With this corner here where we are still trying to fight to really approach that transition. So I would say the minute that we have some simulations that have crossed this green point in equilibrium, where you can take reasonable scaling with them and the phase transition survives, I think it's the minute when we can answer that question for 3-dimensional models of supercooled liquids. Of course, I'm not telling you this, but we are working hard on this to reach that green point and solve that problem numerically. We have super nice results for super small n. So for small systems, we can now do this. And of course, the last question will be, can we do it for larger and larger systems? Can I give you convincing evidence of a positive answer to that question? You will have to reinvite me in X years, I think. Thank you very much.
you, Ludovic. Time for questions, comments. Usually,
Yeah, you have to separate the configurational entropy from the vibrational entropy. I wonder if that is not a problem, especially for very large dimensions, because the vibrational entropy should destroy a solid in the limit of infinite dimensions.
So we need to be careful with the mics. So I have the hand on the button in case it starts again. Yes and no. I think vibrational entropy has been an issue for years in that field, and I have done lots of work to understand its properties. I won't tell you that it's totally boring or not important. I have worked several papers on it. If you followed a little bit the argument that I mentioned is the minute you go to this construction of the transparency potential, this free energy, the quantity you measure, it's not longer an entropy at all. You don't have to subtract anything from anything. So we don't do these measurements anymore in an ideal world. We go to these free energy measurements of V versus Q, and we measure that difference. That's it. There is no notion of a crystal, no notion of entropy, no notion of vibrations. It's done. It's there for you. It's all. And if you think, I could explain to you in private later, if you think about it, there are good reasons to understand that that construction solves all of the problem by magic. It's very efficient to solve that problem.
Yeah, maybe related to that, in experiment there is 0-point motion. How does this play a role? Or how does this enter this problem?
Say that again, just to
In
be
an
sure.
experiment, you always have a 0-point motion, so which gives you an energy which is of the order of the Debye temperature, which is pretty high.
I'm not sure I follow what you want me to say.
I mean, quantum mechanics
Yeah.
have some dynamics, right? Which is 0-point dynamics.
And so what are the, okay, yeah, now I get the first part.
How does this relate to this? To this?
Well, okay, so I think everything I tried to tell you today was about these TK, so far from zero temperature that I think you want to investigate. I think what the part of the calculations that have not been done satisfactorily is imagine that you have that phase transition and you can compute everything about it in large dimensions, and now you enter the glass phase. Can you use statistical physics to predict any physical property in that glass, in particular as you go to low temperature, I think as you want to do. At some point, you're right, we will need to understand enough of these constructions to know how to quantize everything and understand the zero temperature properties. So the short answer is, I told you at the beginning, the analog of the Debye-Einstein, where you take the phonons, which are the excitations, you quantize, you do the stat mech, and you compute the specific head. That part of the work has not been done yet. Okay, so the only thing we are trying to do to go into this limit is we can use sometimes classical simulations to detect the excitations that we can then quantize, and this is where we try to work on the two-level systems, for instance, that Miguel has investigated experimentally. We are trying to do this, but in terms of going to very low T, doing the quantum mechanical calculations, we are very far from anything realistic, because quantum simulations are super complicated on systems that we don't even understand well at the classical level. So it's a difficult question you were asking.
No, thank you. I'm not an expert on the field of so, but if I understand it correctly, your approach will be very appropriate for disorder alloys versus order alloys, because they're actually we are comparing how these different configurations are close to each other. I don't know whether that's contribute something to this problem.
So again, I'm not 100% sure what systems you have in mind.
I'm thinking of the very most simple system I can think of regarding aluminum oxide,
Okay.
right? Which is not a crystal because it has the 3 atoms and there are different configurations. So it's
Yes.
an ordered crystal, is not a glass, of course, but there I don't know, you want to study how the statistical mechanism of the system is, the thing that you are doing, comparing different configurations, is evident.
Yeah, you're asking again, I'm very far from what you're saying. I think all the models that we study in computer simulations are alloys because they, if you don't take alloys in the computer simulations, what you get always is a crystal. So we have to make these things more complicated always. So what we study is the glass transition of alloys usually, most of the time. So everything I've showed you in a sense can be considered as being alloys. I never showed you a Hamiltonian of anything. I just told you I do simulations. I didn't specify the models, but they are multi-species systems, and this is what we use to avoid the crystal as much as we can. So maybe this is the part where you don't like it. Is in everything I said, really the crystal is totally absent because we only work nowadays in those simulations on systems for which we know how to very efficiently suppress the crystal. So it's existing in the other room, but not in mine. And this is why I do my research. And so all the time when I give a talk on glasses, someone likes the crystal, I don't. Because it's polluting everything I do. So, if you want to answer a specific question, you don't mix two questions, but I know it's an important question experimentally, of course.
Sorry, coming back to the phase transition, something that I'm not sure to be understood correctly. I mean, you understood the mean field, the analytical first part in infinity dimensions, when obtain a first order transition with a critical point, etc. Then, especially when analyzed with your computer in 2 and 3, especially 3 dimensions, you can say that is again a first order transition. But this is that's what I'm not sure to understand, because in the past, before all these theories, etc., one idea that, there's a group, as you said, of people say this is kinetic transition, not phase transition at all. And the first idea of the ideal glass transition is that the Kazman paradox, and this a point at temperature, Kalman temperature, where the extrapolation of the configurational entropy goes to 0. Then people spoke of reason that was a second order transition in the sense that was 0 entropy, no discontinuity of entropy, and no latent heat, etc. So it looks like a apparent second order transition if it exists. But really, this kind of mean field analysis, not only in infinite dimensions, goes to a first order transition. How to reconcile first order, second order, how to read with a critical point.
Yeah, you're right. I was a bit sketchy here. I think I told you, and this is why I think I confused you. I told you if you do that construction, it's looking like the first order transition of the first slide. So this is where I think I misled you a little bit. The reason I misled you is I told you, it's interesting to look, as usual, when you have a first order like transition, if you want to understand the free energy difference between the metastable phase and the stable one, and then when you cross, this is coexistence. This is all true. The difference, and this is the question, is that if you think a bit and you go through the details of the derivation, the free energy difference between the two phases, it's an entropy. So it means you have an entropy difference that goes to 0 by Kazman transition, and then the specific heat is different. So you're right. If you want to push the analogy with my first slide and you say I have first order transition, I have second order phase transition, and I learned from the test books what all the thermodynamic quantities are doing across the one and the second phase transitions. This one has a mixed order. Okay, so it's a little bit first order, but from the viewpoint of the specific heat, it looks like a continuous one. So it has a mixed, and you're correct into this, it has a mixed first order, second order phase transition. I didn't tell you about the last part, but this is the reason why people have called that guy the random first order phase transition. And the random into it is to tell this mixed first, second order difference. So it has a lot of things in common with true first order, but at the level of the specific heat, you're right. The specific heat is behaving as in second order phase transition for pure systems. And because of this mixed character, we call it a random first order transition.
Random is the origin of this apparent empirical second, but
so random is a way to remember that it's not exactly a first order transition. I didn't say anything about it, so it's normal that I confused you.
More questions?
And I have a, maybe it's naive, but you were talking about the 2D case where you don't see a phase transition.
Yes.
And when I think of 2D and forbidden phase transitions, I think of the Mermin-Wagner theorem. But I
Yes.
think that is for solids. Is this related or some kind of extension or something?
It's a very good question. I would say it's not a naive one.
Okay.
I think there are at least two theoretical reasons to think that glasses don't exist in two dimensions. The first one is this analogy, or at least this very strong connection between the physics of glasses and the physics of the random field Ising model. In the random field Ising model, the phase transition disappears into dimensions because fluctuations and disorder kill it. Okay, that has nothing to do with Mermin-Wagner. But the connection to the random field Ising model in that approach already says there is a good reason for glasses not to exist. It's the random field Ising model physics. But then you come and you say, okay, maybe you got it wrong. It's not the random field Ising model. Maybe the phase transition would exist to something like a solid disordered state, a true one. Then you come and you say, it can be true because I know that in 2D, perfect order doesn't exist because of the Mermin-Wagner theorem. So what people have never tried to do, everybody knows it in our field, but we don't talk about it because we don't know how to use it to, say, introduce those fluctuations in two-dimensional calculation of glasses. We are so far from doing this. It means that if I take everything I know about all the systems and the statistical physics, if we got it wrong and something like a phase transition exists in 2D, it will be between a liquid and the analog of a quasi-long range order crystal. It would be a quasi-long range glassy phase, perhaps, but nobody has talked about their properties. We all know that, yes, it's probably true, but and lately people were doing going to the other directions some more. People have done two-dimensional experiments, for instance, in colloidal systems. So when you form a colloidal crystal in two dimensions, you have your conventional colloidal crystal. You have a disordered solid in 2D. So the particles are disordered, but the system is kinetically arrested. So people have looked at fluctuations of that disordered solid state in 2D, and they have seen the Mermin-Wagner fluctuations you mentioned. So that observation is just validating your question and telling us that if something like a phase transition exists in 2D, it will be between a liquid and something that doesn't have long range, but perhaps quasi-long range glassy disorder state.
Thank you.
Yeah, thank you very much for the clear talk. I wanted to ask you, is it possible to study the dynamics with an effective Fokker-Planck equation or something like that?
Dynamics. Okay, so that's the topic I didn't want to go into. So, as I said, it's so people spend their lives thinking about the dynamics of glasses. So it's a good question. In that talk, I intentionally didn't go there. Now you want to say I want to predict from simple model and from statistical physics, I want to predict the time evolution of my distribution, which is what the Fokker-Planck equation is about. What you want to do is you want to say, I want to study a system that I know is undergoing a glass transition, and I want to study not the entropy or anything. I want to study, how particles move on average. This is your question, and it's a gigantic field. And again, by analogy with conventional statistical physics, if you remember that computing static properties is complicated, the dynamics, even in simple systems, it's always more complicated. So it's the same for us. The statics here, it's awfully complicated. The dynamics, it's even worse. And so in the framework of these large D calculations, people have done at least that thing. They have been able to compute exactly the dynamics in large D in the way you were suggesting, writing the analog of Fokker-Planck equations and everything. So the dynamics in large D can be solved exactly. And nicely enough, it has lots of connections to theories that people have used in the past, called mud-coupling theory for the glass transition, etc. In finite D, your program is dead. It's too complicated. You need approximations. Which one is the best? Which one is good? We don't know.
Okay, thank you. I think there's no more questions. So thanks to all of you for coming, and especially
Thank you.
our speaker Ludovic for his night talk. And that's all. We close this session.